Imagine discovering that everything ever seen, every star, planet, mountain, ocean, and living being, amounts to less than a rounding error in the cosmic ledger. Every atom in every human body, every grain of sand on every beach, every galaxy captured in the deepest telescope images contributes to only a tiny fraction of what actually exists. According to decades of astronomical measurements, ordinary matter makes up only about 5% of the universe. The remaining 95% is invisible, undetectable by light, and profoundly mysterious. It shapes galaxies, stretches space itself, governs cosmic motion, and quietly determines the ultimate fate of everything that exists. This unseen majority goes by two names that sound similar, but represent radically different forces: dark matter and dark energy. Confusing them is easy. Understanding the difference could change how you see the universe. The modern picture of the cosmos is not built on what can be touched or seen, but on what can only be inferred through motion, gravity, and the behavior of distant light. Telescopes scanning the heavens reveal stars orbiting too fast, galaxies holding together when they should tear themselves apart, and an expanding universe that is not slowing down, but speeding up. Measurements of cosmic background radiation, galaxy surveys, and supernova distances all point to the same unsettling conclusion. The universe does not behave the way visible matter alone predicts it should, as if it is quietly ignoring the rules written for it. These contradictions forced scientists to confront an uncomfortable truth: something enormous is missing from the equations. That realization gave rise to two of the most important ideas in modern cosmology. To fully grasp what dark matter and dark energy are, it helps to understand what they are not. They are not exotic forms of ordinary atoms hiding in the dark, waiting to be illuminated by a better telescope. They are not black holes, clouds of dust, or undiscovered planets drifting silently between stars. They do not glow, reflect, absorb, or scatter light in any measurable way. Their presence is revealed only through their effects on motion, gravity, and the large-scale behavior of the universe. One pulls, the other pushes. One builds structure, the other stretches space itself. As this story unfolds, the distinction between these two forces becomes clearer, and so does the reason they are so often confused. Both are invisible. Both dominate the cosmic energy budget. Both were discovered indirectly through their influence on cosmic motion, rather than through direct observation. Yet their roles could not be more different, and mistaking one for the other obscures how the universe actually works. If unraveling the hidden architecture of the universe sparks your curiosity, stay connected. Subscribe, like, and turn on notifications to follow more journeys into the deepest mysteries shaping reality. Dark matter enters the story first, long before dark energy ever became a concern. In the early 20th century, astronomers began carefully measuring how stars orbit within galaxies. According to Newtonian gravity and later Einstein's general relativity, stars farther from the galactic center should move more slowly, much like planets in the outer reaches of the solar system. Instead, observations revealed something profoundly unsettling. Stars at the edges of galaxies were moving just as fast as those near the center. By all known laws of physics, galaxies should have torn themselves apart billions of years ago. The same problem appeared on even larger scales. Galaxy clusters, bound collections of hundreds or thousands of galaxies, showed gravitational forces far stronger than what visible matter could explain. The galaxies within them were moving too quickly to remain bound unless vast amounts of unseen mass were present. Swiss astronomer Fritz Zwicky was among the first to propose that an invisible substance was holding these clusters together. He called it dunkle Materie, dark matter. Decades later, increasingly precise measurements confirmed his suspicion. Gravitational lensing, the bending of light from distant galaxies as it passes massive objects, revealed gravitational fields far stronger than visible matter alone could produce. Entire maps of invisible mass could be reconstructed by tracking how background galaxies appeared stretched and distorted. Computer simulations of cosmic evolution showed that without an unseen scaffolding of mass, galaxies could not have formed at all. Dark matter was no longer a speculative idea, it was essential. Dark matter behaves like matter in one crucial way. It has mass. It exerts gravity. It clumps together under its own gravitational pull. It forms vast halos around galaxies and long filaments stretching across the cosmic web. These invisible structures act as gravitational wells, pulling ordinary matter into them over billions of years. Gas falls inward, compresses, and heats up. Stars ignite. Galaxies take shape. In this sense, dark matter is the cosmic architect, laying down the framework upon which everything visible is built. Yet despite its overwhelming gravitational influence, dark matter interacts almost not at all with normal matter. It does not collide, emit radiation, or form atoms. It passes through planets, stars, and human bodies without leaving a trace, as if everything familiar were almost transparent to it. Trillions of dark matter particles are thought to pass through each person every second, completely indifferent to walls, planets, or biology. Experiments deep underground and detectors cooled to near absolute zero have been designed to catch rare interactions between dark matter particles and ordinary matter. But so far, dark matter has remained elusive. Dark energy, by contrast, entered the picture far more recently and in a far more dramatic way. In the late 1990s, two independent teams studying distant supernovae expected to measure how cosmic expansion was slowing down due to gravity's pull. Instead, they found the opposite. The universe was not just expanding, it was expanding faster over time. Gravity was losing the argument on the largest scales imaginable. This discovery shocked cosmology to its core and fundamentally altered the scientific understanding of the universe. It earned the Nobel Prize in Physics and introduced a new dominant player in cosmic evolution. The force driving this acceleration was named dark energy, not because it is dark in the traditional sense, but because it is unknown and does not interact with light or matter in any familiar way. Unlike dark matter, dark energy does not clump. It does not form structures or collect around galaxies and clusters. It appears to be uniformly distributed throughout space itself. As space expands, dark energy does not dilute the way matter does. Instead, its influence remains constant or even grows stronger, meaning the universe effectively manufactures more of the very thing pulling it apart. Dark energy behaves less like a substance and more like a property of space itself. The leading explanation connects it to Einstein's cosmological constant, a term he originally introduced to keep the universe static and later abandoned. In this view, empty space possesses an intrinsic energy that exerts a negative pressure, pushing space apart. As galaxies drift farther away from one another, the expansion accelerates rather than slows. Other theories suggest dark energy could be a dynamic field that changes over time, sometimes called quintessence. Still others propose that gravity itself behaves differently on the largest scales, requiring modifications to Einstein's equations. What all explanations share is uncertainty. Dark energy has never been directly detected. It is inferred entirely from cosmic expansion, the large-scale distribution of galaxies, and the relic radiation of the Big Bang known as the cosmic microwave background. Here lies the critical distinction. Dark matter pulls inward through gravity, drawing matter together and shaping cosmic structure. Dark energy pushes outward by accelerating the expansion of space itself. One acts as cosmic glue, the other acts as a cosmic repulsive force on the largest imaginable scale. One shapes galaxies, the other determines the ultimate fate of the universe. The difference becomes clearest when imagining the universe as a growing web. Dark matter forms the threads, drawing matter together into dense knots that become galaxies and clusters. Dark energy stretches the web, pulling those knots farther and farther apart over time. Without dark matter, the web would never have formed. Without dark energy, the expansion of the universe might have slowed, stalled, or even reversed. The balance between these two forces has changed dramatically over cosmic history. In the early universe, dark matter dominated. Its gravitational pull allowed tiny fluctuations in matter density to grow into stars, galaxies, and large-scale structure. As billions of years passed and space expanded, dark energy became increasingly influential. Around 5 billion years ago, it overtook gravity as the dominant force governing cosmic expansion. This transition marks a turning point in the universe's story. Galaxies that are not gravitationally bound to one another will eventually drift beyond each other's reach. Future astronomers, if any remain, would see fewer galaxies in the night sky, not because they vanished, but because space itself carried them away. Over unimaginably long timescales, the universe may approach a cold, dark state known as heat death, where stars burn out, matter decays, and space expands into near-total isolation. If this deep dive into cosmic forces is opening new perspectives, take a moment to subscribe, like, and turn on notifications so future explorations into the universe do not slip by unnoticed. Despite their dominance, dark matter and dark energy do not solve all cosmic puzzles. Instead, they raise deeper questions about the limits of current physics. Neither fits comfortably within the standard model of particle physics. Both may point toward entirely new frameworks governing reality, from hidden dimensions to unknown fundamental forces. Dark matter experiments continue to refine their sensitivity, pushing deeper into unexplored territory. Space telescopes such as the James Webb Space Telescope help map galaxy formation with unprecedented detail, indirectly tracing dark matter's influence across cosmic time. Surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time aim to chart billions of galaxies, offering new clues about both dark matter and dark energy. Meanwhile, measurements of cosmic expansion have revealed tensions between different methods of calculating the universe's growth rate. These discrepancies may hint that dark energy is not constant after all, or that gravity behaves differently on vast scales. Each possibility would reshape fundamental physics and alter predictions about the universe's future. The confusion between dark matter and dark energy persists largely because both were discovered through absence rather than presence. They are named for what cannot be seen, not for what they do. Yet their effects are distinct, measurable, and profoundly important. Dark matter explains why galaxies exist at all. Dark energy explains why the universe is accelerating apart. In simple terms, dark matter is the reason there is something structured rather than chaos in the cosmos. Dark energy is the reason that structure is slowly being pulled away from everything else. One governs formation, the other governs destiny. Understanding this difference reshapes humanity's place in the universe. Everything familiar, stars, planets, life itself, is built on a foundation dominated by forces still not fully understood. The visible universe floats like foam on a vast ocean of the unseen, guided by rules still being uncovered. Future discoveries may reveal that dark matter and dark energy are connected in ways not yet imagined. They may emerge from a deeper theory of space-time, quantum fields, or dimensions beyond perception, or they may turn out to be signals that current assumptions about gravity and matter are incomplete. For now, they remain two of the greatest scientific mysteries ever encountered. One binds the universe together, the other pulls it apart. Together, they tell a story far larger than anything visible, a story written into the very fabric of space and time. Solving either one would not just answer a cosmic question, but rewrite the rules that govern reality itself. What questions do these unseen forces raise about the fate of galaxies, stars, and life itself? Share your thoughts, subscribe, like, and turn on notifications to continue exploring how the universe works, why it matters, and what may come next. This is Tech Mythos.